I mentioned that typically ridge regression is more preferable to subset selection because subset selection simply throws away everything. Unless you are in a very trivial situation like where you have measured the same height in both inches and centimeters, which is a pretty stupid thing to do, no one would really do that. Usually, even two correlated columns of X will each have some additional information content. So throwing away any one of them is not a very good idea. Instead, you should take everything into account, and that is why ridge regression is generally preferred. However, there are certain situations, especially in some modern application of statistics, where P is very large, where you have many columns in X, and then it is usually good if you can just work with a smaller number of columns, because you have just collected data on every conceivable variable and you want to get rid of many of them, only you really do not know which one to get rid of. Now, if you try to do something like all subset selection, that is very difficult. If P is large, then 2 to the power P is even larger, and you cannot really do that. Then there is a variant of ridge regression called the Lasso, which is very useful, and this is by far the most popular technique to deal with multicollinearity in the modern era. This is very similar to the formulation of ridge regression that we saw just now, the soft-bound formulation, the hard-bound formulation. The hard-bound formulation there was putting the hard-bound on summation beta j squared, but in this case we shall put the hard-bound on the L1 norm, namely summation absolute value of beta j less than or equal to some delta. So this is just the same old story, but in this case we are minimizing still the L2 norm of the error subject to a bound on the L1 norm of the coefficients. If you do that, then two things happen. Number one, the problem becomes computationally much more difficult. You do not have any analytic solution for this. However, it is possible to get a computationally efficient way of doing it. So that's how softwares will do it. So with a computer, that's hardly any problem. However, the additional advantage is the minimizer beta will have the extra property that many of the beta j hats will be actually equal to 0. And that is a great advantage because now you have a sparser representation. So usually Lasso gives sparser fit than ridge regression. And this is considered a great advantage because it combines the effect of both subset selection as well as ridge regression. And when you have too many regressors, that makes the final model easier to interpret. So let's understand what that really means. Suppose you are fitting ridge regression and these are the magnitudes of your coefficients. So this is beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat, etc. And a small circle means the absolute value is small, a larger circle means absolute value is large. So when you are fitting ridge regression, you will see something like this. All the beta j hats are present, none of them non-zero. They're all little things. So this is sometimes more difficult to interpret. So all the things contribute a little. Now how do you really interpret that? For example, suppose you are trying to measure, say, the sizes of frog. So that is one thing that one natural scientist was once trying to do. You are trying to express or explain variability of something in terms of sizes of frogs. So the study was about frogs, and in order to measure size, you can measure lots of things. You can measure its length, its weight, the maximum length that it can jump. All these things relate to the size of the frog. Now if you have a little weight for everything, then the individual weights are difficult to interpret. But if you do the same thing using Lasso, you will see that there are few of the beta j's which are significant and large, and the remaining things are simply small, they are simply absent. So now you can describe the same model easily in terms of a smaller number of variables, which is always easier to interpret. So that is one advantage of Lasso. It is called a sparse fit because most of the coefficients will be 0. And when you have many regressors, and in the modern days it is not uncommon to have something like 100 regressors, then dropping most of them will be actually something that is simpler, yet it is not something just dumb like subset selection. You are not doing one thing and then another thing, then one thing and another thing, like a stepwise selection procedure. At the same time, you are not going through the entire difficult thing of going through all the 2 to the power p many subsets. So the Lasso regression is by far the most popular technique of dealing with multicollinearity.